Wix hosts more than 250 million websites. We host over 6 billion requests of media assets every day: videos, images, audio stream, etc. Our system contains dozens of petabytes in storage for those files. Do you want to know how we do it affordable, fast, and reliable? Today, together with Eli, we will talk about the media world, various aspects of it, and the code architecture behind the scenes. So, Eli, maybe we should start with explaining what media is, right? You have a lot of experience in this domain.
Yeah, and media is an interesting thing to describe and talk about. So, what is media, like in a general concept, and what it is in computers, and what it is in Wix?
And what's the meaning of the word?
The meaning of the word media, it comes from the Latin word or the Latin concept medium, which means something through which information is passing and it affects the information in some way. So you can have a medium, you can think of a person as a medium where an idea goes through his mind and is expressed differently when it goes through the person.
Okay.
In the same way, we can talk about images and videos as these mediums or pipelines of information that are transferring visual or auditory information. And this is what we have in Wix, also in media platform. We have these three types of medias: videos, images, and audio, and some more.
Yeah, but we'll not discuss about the others.
Maybe in the end we'll get to them too, but they are less relevant to this conversation.
It's more arbitrary.
Yeah. And we have this very robust infrastructure to support the serving of these media elements to customers of Wix's platform.
Yeah, maybe I'll ask you about, so you said images, right? And like I remember as a kid, I used to save images to my computer and it always asked me like, you want it to be a PNG or JPEG or all those formats? And I had no idea what's the difference. So maybe it's worth like explaining a little bit about those formats.
Sure. When we want to describe some kind of visual information in the format of an image, we have several options to do so. The first intersection, you could say, is whether we want to preserve the information in a compressed manner or in a non-compressed manner. A compressed manner meaning that we will lose some of the information in the original image, some of the visual information which exists in the original image, we will lose some of it. Usually it will be parts of the image that are less detectable by the human eye. So sometimes you will have an image that is compressed, but will look more or less like the original image.
So maybe if you have like few pixels of different shades of red, maybe it will compress it to the different shade, to the same shade, sorry, and then it can save only this kind of
that can be
pixel.
One option for compression. There are several mechanisms that come to play when we talk about image compression. The most naive type of image compression, and also the oldest one, is what we call RLE, relative length encoding. This is a lossless encoding format, which basically says instead of lining up 100 pixels of green color, one next to the other, I'm going just to say green and 100.
So instead of like index 1, index 2, index 3, all of them are green.
Yeah.
So we have 1 to 3, make it green.
We have green, length 100.
Yeah,
exactly.
Yeah.
And we save a lot of bytes with this, but it doesn't work well for all types of images. Usually it works well for images that are hand-drawn,
maybe background
images, backgrounds, things that are less organic. In nature, you will rarely find this kind of 100 pixel of the same color going forward.
Interesting. So we have the size of the image, which is affected by the compression. We have the quality, which is affected
by the compression.
And then we have the third parameter, which is how what's the cost of actually a compression, like how hard the computer should process the image in order to do the compression.
Yeah. This is indeed the triangle of image compression. You have quality, speed, and size. These are the 3 points. Each one is pulling in its own direction. More size means more quality, usually, but also more CPU, which means more time. Less quality means less size, but can also mean more time, depends on the encoder. And generally speaking, we have these families of encoders, which are basically arranged by some kind of historical order, which conforms with the ability of the hardware to perform at the time that the encoder surfaced. So, for example, you have JPEG, one of the old encoders, and it's been around since the 80s, I think, maybe even 70s. I think it's early 80s. And at that time, you had computers with like 64 kilobytes of RAM total, the entire computer, and you have 10 megabytes of hard disk. And your CPU is only at the speed of 4.7 megahertz, not even gigahertz. So the amount of resources you can invest in compressing images is limited.
Yeah.
You don't want all your computer to be compressing images all the time. You don't want to wait for it for too long.
And there was no GPU back then.
No. This is long before the GPU. So these encoders were developed back then. So they're super efficient, really, really efficient, because they had to work on that kind of hardware.
Yeah.
And then we have, at the other end, we have the modern encoders that we see today, like WebP and AVIF and these type of encoders, which allow themselves to consume more CPU resources because we have them today.
And then you get it.
In favor of better compression.
Yeah, better compression means higher quality with a low size.
Exactly.
Yeah, nice. Maybe it's worth, maybe we should go for the place where we have image, right? And then we have video.
Mm-hmm.
And the fact that video is not just set of images. Because we have GIF. GIF is actually an image, it's not a video.
It's a sequence of images, potentially, if you use animated GIF.
Yeah, because then the website doesn't treat it as a video, because it doesn't have the property of the features of a video. Because in order to store a video efficiently, you don't want to save each image independently, but actually store the diffs between each frame.
Correct.
So if you have a forest full of trees, and then you have a giraffe walking by those trees, you don't want to re-render the entire forest behind the giraffe every frame. So you just change the block which the giraffe walks by, and you leave the entire forest behind, just the same.
That's true. And it's also, you might not even draw all the blocks of the giraffes each time, if it repeats itself all the time.
If only the tail moves, so just the tail.
You will paint these parts that have changed. Usually it will be if the lighting has changed during the running of the giraffe or something like that. In video, this whole thing takes a three-dimensional shape when we have also the time dimension. Okay, so it's like a frame that is being pulled over the time to create this kind of a sequence of frames. So when we look for these blocks that are similar, we can look for them inside the same frame, which is like we do in images, and we can also look for them in the video field in other frames in the sequence.
Okay.
So when I come to display me as the player in the front end, when I want to render the video, I will get these blocks coming in, encoded blocks. And when I decode them, part of the decoding will be to reference blocks from previous frames, for example.
Sure.
And display them in the current frame.
Yeah.
It can also mean taking information from a frame that is in the future and rendering it now.
Yeah, and it saves you the data, right? You need less data in memory. That's what it's...
That's what, sorry?
Less data in the memory.
Yeah, the whole idea, of course, of compression naturally is to save data. How we save data? By referencing existing data instead of duplicating the data. Yeah. In video, it's much more effective. It's also much more needed because of the volume, but it's also correspondingly much more efficient because we can also utilize the time dimension for better compression. And this is a huge savings. Think of a scene where you have skies, blue skies. You always have them.
Yeah. And 20% of the video is sky, so you can...
It's like 30% more, or 20-30%. And usually they will not change over the course of a scene, Not the whole movie, but of a scene. The sky will not change, most likely, and you will have almost 100% of the blocks describing the skies and the clouds will be repurposed for upcoming or previous frame.
In Wix, we don't, as a media platform, we never choose the format for our users. We have the defaults that we believe is the most efficient one in related to the quality it supplies. But it's for our developers that works with us to decide which format they want, right? If they want to encode from PNG to JPEG or from WebP to AVIF, we just give them the option to do so.
Yeah, it's totally up to the user of the platform to determine these things according to what's the application that is working. And generally speaking, when we talk about Wix media platforms, the customers, so to speak, of our platform are Wix developers.
Yeah.
The way that Wix handles the structure is that we have this vertical application teams that are building applications, and all of these teams are actually using media platform for their media needs.
Yeah, we assume that they know something about media.
We assume, and we also help them when it's
sure.
needed, but we rely on them to say what they want to do, and we don't decide it for them. So, for example, we allow them to upload any type of media that they want and declare the content of the media according to the way that they know about it.
Yeah. As we discussed, like in the previous episode, we discussed about our platform being unopinionated. So that's a good example for how we do that. So they know what to do. We just give them the platform to do so.
Yeah, this is one of the, you could say, the founding guidelines of our platform, which we call unopinionated platform. It means we make as little as possible decisions for our caller on behalf of our caller, and we let them upload the medias that they want and create the manipulations that they want on it, and we just try to perform whatever was asked of us. And this is not a black and white situation. Okay? There are some points where we need to protect our platform, for example, so we can reject certain types of files that we can suspect are malicious, for example, or just exceed some kind of
size
resource requirement, can be size or whatever like that.
Right. So we know about encoding, but we have other capabilities as well, right? Our videos has the VOD, the posters, the storyboard, the live stream. Maybe we should talk about it. The VOD is an interesting component we host.
So we have, the platform basically has two main functions. Each of them is huge, okay? But generally it comes down to two functions. You can ingest your files into the platform, upload them, and you can consume them in different ways. So when we talk about uploading, the upload part is pretty straightforward. You have this mechanism for uploading. You can choose between several mechanisms of upload. We have the standard upload, we have multi-part upload, we have resumable upload, and all these types of uploads.
The TUS algorithm.
Yeah, the TUS algorithm.
Protocol,
the protocol. So, and after the file uploads, it automatically gets ingested into the system, which means its metadata is being extracted. Some characteristics of it are being extracted as well. Sometimes we will send it to some machine learning models for tagging, like auto tagging for images and videos.
Yeah, super cool. Internally in Wix.
Internally in Wix, yeah.
The AI algorithms is
the models are internal to Wix. The whole AI offering, which is happening big time in Wix right now. I can't speak about everything that's going on, but it is
in the next podcast, maybe.
Yeah, it is all internal inside Wix. So this is the ingesting part.
Yeah. So the user, like the developer of Wix, which is our client, knows the metadata of the video, of the file after he uploaded it.
He can query it, he can query the platform.
And then he can do all sort of stuff according to this metadata. So if it's a video and it's codec, or like if it has some transparency aspects, then he can transcode it in such a way that is appropriate to the specific video.
Yeah. So apart for uploading, if we talk about videos, the user, our user, which is the Wix development teams, can decide how they want to serve the videos to the users of their vertical application. So we give them the ability to transcode the video into several
different
options.
Qualities, maybe.
First of all, we talk about different qualities, similar to what you may see on YouTube.
Yeah, that's a very cool feature because
platforms. Yeah.
I never knew that. That's like how it works behind the scene until I came to this team.
Multi-level.
Yeah. So in YouTube, you always have this option, the button on the bottom right, that can choose the quality. It can be 360 pixels or 480. Like there's different resolutions. And then behind the scene, what actually happens, the video is transcoded into a few different qualities.
Yep, correct.
And the browser or the client knows how to choose the relevant quality according to a protocol called HLS protocol.
It's a combination of several things. HLS indeed is the facilitating protocol for this process, but the decision which level to choose is done on the player side.
On the client side.
When it is sampling the quality of the internet.
And that's what we call adaptive bitrate.
Adaptive
right?
bitrate. It's called ABR. The multi-levels are called an ABR stack. All of them stacked one on top of the other.
Yeah.
And what it is basically the same video stream that the user uploaded to our platform, which is encoded into several bit rates and consequently qualities and resolutions. So when we have these several bit rates, we produce this HLS manifest like you described, and the player in the browser usually will know to switch to the correct level according to the current internet climate, you could say.
And that's how, if you go into the car and you watch like a video in a phone, you're not driving obviously, but as a passenger, you watch a video in a phone and then you go into a tunnel. And then immediately the bandwidth goes
down.
So you see the video goes pixeled, and then when we go out of the tunnel,
it depends on the tunnel. You know, some tunnels you get a dead end, no link at all. But if you go through some environment that has noisy radio frequencies, multiple buildings, some kind of masking on the radio signal, maybe even some light tunnel, you will get a decrease in the internet speed. The player, if it's a good player like ours, will know to detect this and select the lower level. And it can do this again and again and again until it reaches either the lowest level or a level that corresponds with the current status of the internet band.
So it's not magic. It's just the player knows what's the bandwidth and choose
there's no magic
appropriate and coded video.
It's just good protocols and good implementation. No magic here.
Okay. So that's about our videos, right? Maybe we should discuss the image service.
We haven't discussed the consuming side.
Let's talk about the consuming side first, of course.
Yeah, so for videos, like we said, we have this HLS link, which is the way to consume these videos. We watch them. It's worth mentioning that we have several video capabilities in the platform. One of them is VOD videos, like we just mentioned. The user uploads a video, it gets transcoded into a multi-level ABR stack, and then it's being served with an HLS manifest. That's one thing. And we also
the manifest, maybe worth mentioning that the manifest is like
the manifest. First of all, it's not a Wix technology. The manifest is HLS standard. And what it is basically a list of the various levels that are included in the stream
and their appropriate URLs, so you can just redirect yourself.
And a link to their corresponding manifest of that specific level. In each level, you will have the video stream and the audio streams, possibly streams that are associated with the video, packed in a transport stream format, and that's how the player plays them.
So, Eli, we talked about videos. Maybe let's jump to our beloved image service.
The image service is one of the major heavy lifters of the platform. It takes a huge load every minute of every day, taking care of about 1 million requests per minute. And what it does is provide these various manipulations and transformations on images. And these can be cropping, filling a certain area, blurring, adding a watermark on the image, all the while preserving the original aspect ratio of the image, so you're safe for your website that the image won't be distorted. Additionally, after we've done all these manipulations, we can choose the output encoder in which the image will be encoded. And then we can choose PNG, JPEG, AVIF, WebP, all the formats that AVIF is a new one, by the way. Maybe we'll speak about it later. All the formats that we mentioned. Everything is optimized from the ground up to be super, super, super fast, and all the manipulations are being done on the fly. And it's what can I say? It's a pretty fast piece of software that we're using, and it's supporting, like I said, about 1 million requests per minute.
After the caching layers.
That's a good point. Actually, the way that the infrastructure is built, we have these 6 billion requests a day coming in. Most of them are being served by our CDN, which holds previous copies of the responses to requests. These will be images in various formats. They're being cached in the CDN based on the URL that requested them. The rest of the traffic goes through to our backend and reaches the image service directly. And then all the encoding is done in real time, manipulation in real time, everything is done in real time.
Yeah. And maybe I can't stress it enough how much value it gives to Wix, because as a website hosting service, if the image is loaded fast, right, the page loads fast, because usually image is the most slow component, and then SEO scores rise, and it gives the entire value for our users to provide the website that loads fast and get a good score. So image manipulation is one of the most critical services.
Sure. There is immense value in images, even more than videos, because, well, for several reasons. No matter what the purpose of your website is,
it has images.
I will take, for example, e-commerce websites. If your image loads in more than, I hope I'm remembering the numbers correct, more than 250 milliseconds, there is more than 60 or 70 chance that your shopper will bounce and will not even look at the product because it takes too long to load.
Yeah.
So these things have immense value, business value, and additionally, it's user experience value. If you want to keep your users happy and smiling, you're not going to serve websites that take ages to load, specifically images, because it's, you get these empty squares.
So we must compress the image, and we must do it fast.
You must compress the image, you must do it fast, and the result of your compression must be small enough to reach the browser fast enough.
Yet look good. Yet it should look good.
Above all, it should look good. Yeah. The quality is a major thing. And that's why we're constantly, or not constantly, but once in a while, it's not that this kind of thing happens all the time, but when there is a new image format that can give us more value and our users more value, they can get better images, they can get faster images, we definitely will go the extra mile and incorporate this format.
Yeah. And we just did it, like your personal projects a few months ago.
One of them, one of my recent projects and our projects in the media platform team was the incorporation of AVIF format, which is a new format.
We went from WebP to AVIF as a default.
A few years ago, we added WebP, which was also a great improvement over JPEG. And just recently, we added AVIF, which is an even better improvement on top of WebP. What's exciting about AVIF is that it stems from AV1, which is the prominent video compression format today. It has superb quality and quality to bytes ratio, and it's like the perfect video encoder. And consequently, AVIF is also a very good image encoder, which gives us, if we compare it to WebP, we can get the same quality for 50% of the bytes, usually, if we ballpark it.
I'm curious, who did AVIF? Who invented this format?
It's a good question. You should ask who invented AV1.
Who invented AV1, Eli?
AV1 was born after somewhere around 2015, 2016.
2016, 10 years ago.
When HEVC was the prominent, H.265, it's also called, was the prominent video encoder. It was amazing. It had superb quality. It was adopted by all the vendors. Apple put on its iPhones chips that know how to decode this format.
Yeah.
And there was really massive adoption. But small problem with this.
The license.
The patents and the license, HEVC, amazing as it may have been, it still is, but not being used that much, was a bundle of spaghetti of patents owned by various groups that took part in the development of the codecs. So if you want to use HEVC, you have to ask yourself, which algorithms am I using from HEVC? Am I using 5 of them? And then make a list of these algorithms, and for each one, you have to pay royalty to a different group that holds the patent for that specific algorithm.
So if you want them, you need to go to your closest legal advisor.
Yeah, a lot of work for lawyers, but not so much for tech startups. So eventually, it was clear that something better had to emerge because this was burdening the entire industry with this license thing. Apple, okay, it's a giant, so it can put the encoders and pay the fees and it will be okay. But for most of the industry, it was unusable. And then a new alliance was formed to remedy this situation, the alliance is called the Alliance of Open Media, what we call AOM today.
AOM.
AOM. The purpose of this entire gathering was to create a video encoder that didn't have this patent jungle situation.
Open source enthusiasts.
Open source and open patent from both of them are open source, by the way.
Yeah.
It's just whether you're allowed to use it or not.
Yeah.
So, and that's how AV1 was born. The same companies are part of the same, it's the same people doing the encoder, same like in 265, but the incorporation is different because all the incorporations, they state clearly from the beginning that it's going to be open for use. There's no patent issues, etc. And that's how AV1 was born. And like any good video format, if HEVC or H.265 had the HIC and the HIF image formats, so AV1 has AVIF as the image format, which benefits from all the advantages of the video encoder.
And maybe a good point is how we released this encoder, right? Because we did introduce something new. We need our clients to align with us, and we need to check that it works well. And it's not easy to just introduce a new format all of a sudden. It requires some work. You don't want to remove your CDN hit ratio so suddenly. So it needs to be gradual.
Yeah, there are many aspects to replacing a video format. In this specific one, we had several challenges with it. The first one was the implementation of the whole mechanism. Like, how do we implement AVIF encoding in our framework?
Yeah, it took a while until we figured out how to do it quick enough, right?
The situation is that The situation is that the state of the technology today that we are using for the rest of our image operations is not fast enough to encode AVIF. So we couldn't use that existing mechanism, and we had to actually bring a whole new mechanism just for AVIF, and this is libAVIF by the Alliance of Open Media that we mentioned before.
AOM.
So we had to use a different library to implement this, and the challenge was, it's worth mentioning maybe before that the service is, the image manipulation service is written in Golang.
Yeah, and it has this C library.
And it has a C library, which is doing the manipulation heavy lifting.
And then the bridging of C-Go together, so you have the entire repository.
That's a challenge in its own, connecting C code to Go code. You have to use C-Go and you have to do it properly.
But Go has this feature and it's like, it works nice.
Yeah, it works nice, but it means you have to be extra careful about your C code, what's happening. That's just a side note. In any case, in our case, since we used two C libraries, we had to transfer the bytes through Go from one library to the other. Like we have a C library, and then we want to connect to another one. Both of them are connected to the Go code. So in order to pass this memory from library A to library B,
you got to go up through
Go. And this was extremely slow. So the way we... Unless we use the mechanism in Golang, which is called unsafe functions, which basically talks about passing C pointers.
Yeah, it's a built-in library of Go
code.
Unsafe,
it's a built-in library in Go. And it required some changes to the first library that we were using. So it would expose the byte data so we can take it and use it in another library. This pointer that was being exported by the first library is being passed as is to the second C library without doing any manipulation in Go.
So just the raw data of the image.
It's just it's not even the data. It's just a pointer to the data. It's like the 32-bit pointer being passed from library A to library B through the Go code, and then. This solved the speed problems, actually, because in the second library, the AOM library...
It was dedicated for AVIF.
It's a dedicated library for AVIF.
So much faster.
Full control over the entire encoding parameters, and that's how we were able to achieve the speed.
Because maybe our existing library, the problem wasn't like... It's not that it wasn't efficient or something, but it narrowed down the flexibility of the parameters you can control.
Yeah. That was
and then you needed the freedom to... tweak the
library itself is amazing, by the way. It's very fast. It's super optimized. Couldn't be any more optimized, I believe, although you always have a little bit more. But the specific part of AVIF had several problems. One of them was what you mentioned, that the API that was exposed by the library was not enough to get the speed that we need. And the second disadvantage is that even if you used it through the library, you have to go through an additional layer inside, and that like above libaom, the additional layer, which was slightly problematic in terms of maintenance. And it's an open source that hasn't been bumped in versions properly. So we had to do something different, and that was introducing libavif directly into our code and connecting them in the manner that I mentioned before.
Yeah, so we needed to introduce the new libavif in the code, create a new code flow that bypass the existing library, and give it the unsafe pointer to the data in order to process it quick. So that was challenging.
Yeah,
and no bugs, of course.
Of course, we don't write bugs.
Never. And the impact was huge, right?
The impact was huge. We saw a decrease of about 50% in the image bytes coming out of our system. The impact was amazing.
Yeah. And again, the 50% less, I want to stress it again. It's not that we need to send less data that improve the system, as the end users received less data in the end. And sometimes our users lay on not the fastest infrastructure. Maybe sometimes it has a lot of latency. So the smaller the image, the better.
For sure.
It can be huge difference.
Even if you have good bandwidth, you have this internet error rate, you could call it.
Hiccups,
disconnections, reconnections, all these mechanisms. The faster the resources get to the browsers, the less potential problems you can have. Another challenge that we had while replacing or introducing a new image format is that we needed to also invalidate most of our CDN, since the image payloads are different. It's not the same payloads.
So you don't want the same request to return the old encoder, right? Yeah. That was the use case.
Otherwise, we didn't do much if we're transferring the same bits. So what we did is we changed our dialect, the structure of the URL.
Yeah, so the image service has the API through, we walked through REST, is worth mentioning. So we have this REST URL, this HTTP request, which has its own set of commands on top of the image. So you have image1.jpg and then / and then you can ask for less a specific size or specific encoder, stuff like that.
The way that this manipulation works, because the final product of the manipulation needs to be consumable by a browser image tag, we are limited to only one type of requests, which are GET requests. We cannot do POST or anything like that, because browser, unless you're using AJAX, don't do that. Standard image tags don't do that. And that's why all of the commands that configure the manipulation, be it fill, fit, blur, crop, whatever it is, change the site, change the encoder, everything is contained in the URL parameters. So the URL is actually also the key to the CDN. So when we introduced the new format, we also had to make some change in the URL in order to get a different key for the CDN and consequently a different payload for the user.
And as a platform, we don't control the requests. It's our developers to change the requests.
In this case, it was we have this concept of experiments where we introduce new features gradually. And in this case, we introduce this change to the dialect gradually, and also invalidating our CDN like that gradually as well. And we had control over the entire process. So when we open the experiment to X users, we see that the CDN is cleared for these X users, and new data is coming in.
But we did it in such a way that you had to use some sort of new command in the URL that requests specifically AVIF until we go to the point where it's cached. It's out of the cache.
Yeah, but since we want it immediately, we make the changes in the URL because we want them the payload. It's not like it's going to be a different URL later.
No. But I just mean that if you want to AVIF immediately, you just have to add this specific parameter to the URL, and then it gives you the AVIF.
Yeah, we use the feature. One of the features that Image Manipulator has is a feature that is built for browsers, where the browser dictates or declares which image formats the browser supports via the accept header.
Yeah.
All this happens automatically in browsers, by the way. You don't have to do anything. And when Image Manipulator gets this request, he can look at the supported images on the browser and then decide internally on the encoding. So the user, it's like the user saying, give me the best encoding for my browser. I don't want to know what it is. Give me the best thing. And this is the majority of our users, by the way. So the fallback would be, if before it was we try to give them WebP if it's supported, and then there is a list of fallbacks. Now the top of the list is AVIF if the browser has it, and then it's WebP, etc.
Okay. Yeah, that's cool. Maybe we can talk about the image service regardless of the AVIF. So we do have some cool like tweaks and like internal logic to make it work fast and efficient, like the masters.
For sure, there are several mechanisms in place to make it work faster. First of all, it has several layers of internal cache apart from the CDN. Then we have the concept of masters. So when we do, let's say we have a source image, and then we do some manipulations on it.
Yeah.
And the manipulations are dramatically different in size. Let's say one of them is 200 by 200, one of them is 1000 by 1000, and one is...
it's counterintuitive because if you want to, if the source image is 2000 pixels over 2000, and the user asks for an image of 1000 on top of 1000 or 200 on top of 200, then the processing of the image to get it to 200 is much heavier than to get it to 1000, right?
Yeah,
So
that is correct.
There's a value in doing as less resizing as possible.
For sure,
right?
Yeah. The way that the resizing is being done, like roughly speaking, okay, there are several algorithms to do this in various levels of efficiency. We use a very efficient one, but basically what the process is, if you're resizing from factor X to factor 4X, you take each square of 4 by 4 pixels and you make an average, make them into one. So the more ratio you have to downsize, the more pixels you have to calculate the average on.
And then the calculation is more complicated.
Yeah. So it is true that resizing to a smaller difference is faster. And another aspect is, let's say we put it against the option of doing the resize on the client side. It means that, let's say the image is 2000 by 2000 and the browser wants 400 by 400. If we don't do the master mechanism that we just mentioned, the early size preparation that we just mentioned, it means that not only will we pay for resizing CPU in the browser, because we don't do it on the back end, we will also be feeding a large number of bytes into the encoder, which is that's the CPU heavy lifting, and that's what we definitely not want to do if we want to be fast. So we want first to reach the appropriate size, then feed it to the encoder, then serve it to the customer.
So if we'll explain this concept of masters, so every time you ask for a source image in a specific size, there's a constant sized image, right? Let's say 500 on 500. And if the user asks for a 450 pixels, then we'll take the closest bigger master, in this case 500, and we'll resize the source image from this master.
Correct.
So we already have it in cache.
And why do we choose the bigger one?
Always the bigger one,
because
not to lose quality.
We want to lose the minimum amount of information.
Scaling up means you invent pixels.
Exactly.
Scaling down means you use the existing data.
Averaging, correct. So we create this set of masters, you could say, for each image. First of all, we always save the original image that the user uploaded. In case he wants to get it, he can request it and get it.
And even if he wants a bigger size than the largest master, right?
Yeah, everything is possible up to a certain limit in terms of manipulation. So you can ask, it's called superscaling, when you want a size that is bigger than the original that you uploaded. In any case, when we get the requests, we provide these several sizes of masters for each image. And when we have a request coming in, we start the manipulation, like you said, from the master that is closest to the size requested by the user. And then we get minimal amount of processing and also maximum quality on the way.
Yeah. So that's masters. So another caching layer is actually the result itself, because we do have the component of the optimizer. Because two different actions, two different dialects on the same source image can result in the same image eventually.
Correct. So it is possible for you as a caller to request the same operation in two different ways. And this will cause the URL to look different, your request URL to look different. So if we're talking about CDN, it will be two different keys. But when it goes internally to the image manipulation service, there is a mechanism inside the image manipulation service that is normalizing the request for the purpose of optimization. And what it does, it makes sure that if the output of the operation is X, the request will always be X as well. It eliminates the option to have two requests generate the same response.
Eventually, it's all about resizing and cropping.
That's resizing, cropping, filling is also a thing, and watermarking. It's
watermarking.
All the features. It's true for all the features. Eventually, the result is being cached, and the key is the optimized URL. So in this case, we will not miss the cache because the request is different. It will hit the cache in both times.
And it will save a lot of processing inside.
And it does save a huge amount of processing today.
Yeah, which is amazing. We also have the metadata cache. I don't think we need to talk about it.
Yeah, we can talk about it. Metadata. Let's talk about metadata in general. We have several levels of metadata. When a media is coming in, we have the basic metadata. For an image, it will be the width, the height, the encoder. For video,
whether it's public or private, as an example. Some images are private, and we don't want to like every user in the world to access them. And then we have the privacy mechanism, and each request will ensure that the image is public or private, and then the token that's sent with the image is authorized.
Yeah, that's correct. This authorization mechanism it's also an interesting point, by the way. The whole token authorization system.
Yeah, it's another discussion just itself.
Yeah, but we can mention it in two words, because authorization is something that exists in every system, whatever the domain may be. But here we have an additional level of information that rides along with the authentication. For example, you can say in the authorization token that for a specific image, this token allows you to watch it blurred, while another token allows you to watch it unblurred and full quality. And this is very useful for one of our verticals, which is...
DeviantArt is one of the...
DeviantArt is one of them. We also have a lot of pro galleries within the Wix offering.
Yeah. And then you can buy, like you have access to a small version of the image, maybe blurred, maybe a thumbnail. And then if you want to buy the image, like digitally, then you get the URL that contains the original source. And then you're unlimited. Because then you can... control.
It's a great mechanism for any kind of situation where you want to purchase the image and then view it online. So it can be pro photographers if we're talking about image gallery. It can be artists if we're talking about DeviantArt. All these types of images that are protected by some selling point, price that you have to pay, can use this mechanism of blurring and then serving it clearly, and it's all contained in the token.
Yeah, so we have this image service, right? It has CDN layers, it has masters, it has all sort of like new formats that helps resizing it.
For sure.
Okay, we have the permissions concept that allows different users to see only different aspects of the image. How do you test this thing?
That's an amazing question. We have a lot of testing layers, a lot of different testing layers, or quite a few, you could say. The initial testing layer, if we're talking about the image service, is it's actually a bunch of tests or a suite of tests that is connected with the image service, like kind of a unit test, or you could say something along the lines of a unit test. And this tests all the functionality of the image service, along with some special kind of test
called golden.
That we called golden.
And you know why it's called golden?
I actually do know why it's called golden. Yes. In the early days, I'm coming with all these stories about the early days.
We love that.
Yeah, I was there. What can I do? So back then you had this concept in image processing, which was called the golden eye.
The golden eye.
The golden eye. The golden eye is an actual person.
Okay.
It's not a mechanism. It's an actual person that after all the PhDs are doing their things in the compression domain,
engineers.
The engineers, and it's always with one or more PhDs. When you work in image compression, you always have some mathematician, something like that.
They do
MATLAB stuff, and then you have to write the code for that in C.
And then the UX designer or the artist or whoever it is.
Yeah, the golden eye, right. Yeah. So in those days, you had these PhDs doing all their calculations and what they thought was best. And then they have this output.
Yeah, they have an image. Yeah, eventually they came out with
usually it's two images.
Great algorithm.
Before and after.
Yeah.
And then you want to know if it's good or not for the human, not for the mathematical formula. Yeah. And then you bring this golden eye. The golden eye will usually be an artist or a drawing artist, a photographer, something from a graphic designer, somebody from the artistic domain, you could call it. And this person would just look at the image with his eyes. Yeah, really, like just look at it.
Yeah.
And he would say, this is better or this is better. And then all the engineers and PhDs would go back to the drawing board and start working again, or it was good and we move forward.
Yeah. So we kind of copied this mechanism.
Yeah, we copied this principle of golden eye, and we have what we call golden test. Golden test is actually a test that takes an image, runs it through a certain manipulation, and then makes sure that the output is identical to the expected output. And when we say identical, it's not like x equals 5.
It's a bit more complicated.
It's a bit more complex. It's all the bits of the image. Let's say the image weighs, 300 kilobytes, just for example. All 300,000 bytes have to be identical for this test to pass.
Yeah. But we have all those layers because sometimes
this is the initial layer, the most strict one. If this test passes, you don't need to continue anywhere.
But if it fails,
we have to move to a different kind of test, which is not... It's not like a byte equality test. It's more like a equal visibility test.
It looks close enough?
The image looks
is it
close enough or the same.
Yeah.
So
and it happens because if we upgrade one of the internal libraries, then algorithms change a little bit. The color space may
can happen for
many
reasons. Yeah. It can be due to architecture, CPU architecture.
Usually it's better, but yeah.
It depends. We don't have to guess. We have measures for this. When we come to these situations, we compare the images both visually with our own eyes, and we also use algorithms to compare the images, usually to the source images. And then we use algorithms like SSIM, structural similarity, or VMath, which was developed by Netflix, PSNR, MSIE, and all these algorithms that are known in the image processing domain. And if we see too much of a difference in these algorithms, then we need to understand why. Usually it means something was wrong along the way in the process, whatever change was made to the code. But like you said, these changes can also happen for technical reasons, different CPU architectures, different operating systems that contain different library versions.
Yeah.
Can happen for a multitude of reasons. And that's why we have these tests.
Yeah, and that's nice. We have, now that one of the plans in the future is we're working at the moment is trying to break this service into two decoupled services, right? We have the proxy and the processor. So this one is in charge of the HTTP handling, and the other one on the heavy lifting of the images. So now we can use this infrastructure to make sure that when we decouple them, we maintain the same business logic.
What we did with this is actually incorporate a common practice in microservices where you, for the same service, it's a good practice, in my opinion. For the same service, you separate the API layer from the logic layer.
Because that's how intense, and that's a little bit like the profile of the work is a little bit different. The workload, the scaling.
Yeah, what it gives you is, first of all, you have a good separation in terms of the code base, which means stuff is less vulnerable to changes. You also get better throughput because, like you say, you can scale them differently according to the workload that they're getting. Well, the API pod will get only the workload of the APIs, and the processing or worker pod will get the actual work.
CPU intense, like
more CPU intense, and you can scale it more to provide more requests coming in from the same API proxy.
Yeah. And then I try to say that the golden test keeps you like safe in this kind of like change.
Through any kind of process. This is an example of a process, but through any kind of process that we do, including introducing formats, optimizations, fixing bugs, whatever the process may be, it goes through the entire testing chains each time.
Nice. So we can't reach production unless the golden test.
Yeah, so it was great talking to you today, Tomer. And for our viewers, if you have any comments or questions, feel free to drop them down in the comment section below.
Thank you for joining.